Demography, Part B. I want to continue to talk about the demographic characteristics of a population, that is, the overall way we describe and examine a population. One way to continue the discussion about demographics, that is, the characteristics of a population, is to examine a life table. And here we have a life table for Dall sheep at the Denali National Park in Alaska. This life table consists of 4 columns. X, which is the age in years, N sub X, which is the number alive at the start of age, L sub X, which is the proportion surviving as a fraction of the newborns, and D sub X, which is the number dying in a particular age interval. L sub X is survivorship. We'll come back to that later, but I want to emphasize that. So here we see that we have basically from 0 to 14 years. We started with a population of 608 individuals. At the end of 14 years, there are none surviving. The survivorship, as you can see, because remember, it's scaled to the fraction of what we started with, is really sort of a percentage decline. So for instance, from 0 to 1, we go from 608 individuals to 487 individuals. Roughly, the population drops by 20%. We have about 80% surviving is sort of the way you want to sort of think about that. And we go down the line. So this we can use this to characterize a population and to talk more about the population. Now, before you get too worried, we're not going to do a lot of this in this course. That is, we're not going to delve very deeply into life table analysis, but I want you to be aware of what the life table is and be able to look at it and understand what it's describing. As I said, if we take that column L sub X, which is the survivorship, we can explore that graphically by making a graph of the age on the x-axis and the survivorship on the y-axis. And we can use this to look at survivorship curve and to describe populations. If we do that, if we construct these survivorship curves, we're going to find that we can get roughly 3 generalized types of survivorship curves. Now, keep in mind, these are generalized types. And I want you to know them as generalized types, but I want you to be aware that when you look at natural populations, typically there'll be amalgams or combinations of these 3 types, not maybe purely one particular type, okay? So please keep that in mind. Again, if we look at them graphically, we're going to have age or percent of lifespan on the x-axis and survivors on the y-axis. Type 1 survivorship, denoted in the graph as blue and yellow lines, have low survival at young ages, which would be up in this area here. Then we have relatively high survival until we reach old age, then survivorship begins to decline. This is characteristic of many mammals, including humans, and if you stop and think about it, it makes sense. There can be infant mortality. Then once you make it to adulthood, you survive, and most of us die of old age. And that's really what a type 1 survivorship is like. Type 2 survivorship, shown as the orange and sort of darker blue line in the middle, are constant sloping downward. This is survivorship that's constant across all ages. Common in many bird species, we see that basically it means that survivorship, it doesn't change from one year to the other. There's just a constant number of individuals, or I should say more or less a predictable number of individuals that die, predictable number of individuals that survive. Finally, there's type 3 survivorship, in which there's very high mortality as at early ages. Then mortality declines or survivorship increases. They're sort of inverses of one another. If you're alive or you're dead, they're opposites. So what we see here is early mortality is very high, but it decreases with older ages. So we have survivorship dropping very quickly at early ages, then it sort of levels off and sort of approaches the x-axis asymptotically with age. This is characteristic of many invertebrates, insects, crustaceans, such things as that, and plants. Again, you notice that type 1 and type 3 are sort of opposites of one another, and type 2 fall in the middle. Again, I want to stress that these are idealized forms, and we don't see them exactly in natural populations, but they're important for understanding how a population might be organized. Here we have two survivorship curves from natural populations, and as you can see, it's difficult really to characterize them as type 1, 2, or 3. If we look at figure A, again, I would characterize it as type 1. It has a fairly substantial drop in survivorship early on, then a somewhat less drop, that is a sort of stabilization of survivorship through middle ages, and then a precipitous decline at the end. Again, I don't know. You might be able to argue it's a different type, but you get the idea. The type 1, 2, and 3 are idealized forms. Now let's look at the actual text of this particular slide. We see, first of all, that habitat quality can affect survivorship. In figure A, which again is age on the x-axis and L sub x, which is survivorship on the y-axis, we see that this is a deer population, but these mammals have a higher survivorship in the chaparral than they do in the shrubland. Survivorship curves can also differ among the sexes. In part B of this figure, again, age on the x-axis, L sub x survivorship on the y-axis, we see that females have a higher survivorship than the males. So survivorship can be influenced by characteristics of the population, the sexes, or the quality of the habitat, quite honestly, both. Life tables can also be used to calculate other things. For instance, something called life expectancy, which is the far right column, E sub x. What I want you to notice here is that E sub x varies with time. That is, it starts out, in this case, for this plant at 1.38 years, can go up to 1.40, and then it starts to decline again. Don't worry about trying to calculate this. We won't really spend, again, a lot of time calculating these in class, but I just want you to be familiar with how life tables work and what some of the information is you can glean from these life tables. Keep in mind that there's really two things here that we often talk about: life expectancy and lifespan, and they're not the same. Lifespan is the maximum number of years that an individual in a population can potentially live. You have a lifespan of 15 years, a lifespan of 100 years, whatever the case may be. Life expectancy is this calculation, this E sub x, and life expectancy is the expectation of life at a certain age and is affected by the probability to die at different ages. So it's a calculation and it's a prediction. It's different from lifespan. So there's subtle differences, but you understand that that's important. For instance, if we look here at this age-specific diagram, this life table for Belding ground squirrels, you see this is for females, this part of the table is for males. I want to draw your attention to the life expectancy, and again you see that from 0 to 1 year old squirrels have a life expectancy of 1.33 years. If you make it to your first year birthday, your life expectancy goes up to 1.56. If you make it to your second year birthday, your life expectancy goes up to 1.6 years. And then actually stays pretty steady for a number of years. What this means is of course, that there's a higher probability of dying, a lower probability of surviving. Therefore, your life expectancy is less when you're very young. Once you make it to adulthood, then your life expectancy goes up a bit because you've made it past the first hurdle. And of course, it's going to drop off towards the end because you're getting older and old age, and you will eventually pass away. So life expectancy often shows that kind of trend where it's slower, then increases, then decreases with age. And again, remember, it's a prediction of how many years on average you have to live, having made it to a particular age. So life tables can be very useful in looking at the populations from these perspectives. Another demographic characteristic that's important is sex ratio. And sex ratio is simply the number of males versus the number of females. This can vary among various groups in a population and can even vary with different age groups. We typically talk about 4 different kinds of sex ratios. Primary sex ratio, which is sex ratio at fertilization or conception. Secondary sex ratio, which is sex ratio at birth or hatching. Primary sex ratio, which is at sexual maturity, and tertiary sex ratio at sexual maturity, and quaternary sex ratio at adult. And the sex ratio of a population reflects different mortality rates for the different sexes and can really have reproductive repercussions for the population. Here's actually a table that looks at adult sex ratio. So it's sort of a combination of tertiary and quaternary sex ratios. The top species are in red are bird species. The bottom 3 are mammal species. And what I want you to see here is that sex ratio tends to, first of all, in a sort of general trend, if we look at that adult sex ratio, what we see there is they tends to be close to 50-50. Yes, you see some are 60, that's 60 males versus 40% females. Some are 40% males, 60% females, but they're in the close 50-50 range overall. I also want you to notice there are some other patterns here. That is, in birds, we tend to see that the sex ratios are skewed towards males. That is, there tends to be slightly higher male survivorship than females, so the adult populations will be slightly above 50% male and slightly below 50% female. Whereas in mammals, the reverse is true. That is, adult populations tend to be slightly below 50% male and slightly above 50% female. Here's another example of this, looking at elk, mule deer, and mountain goats. And again, looking at the far column, the adult sex ratio, this is the number of males for females, and what you see is that they're skewed towards females. That is, lower numbers of males, higher numbers of females. So the empirical data show that adult sex ratios in birds tend to be male biased. Those in mammals tend to be female biased. And that can have impacts on courtship, on mating behaviors, and therefore on the reproductive health and function of the organisms. How do organisms' populations change in time and space? Well, the way I want you to think of it is here we have this population of birds right here. And there's basically 2 ways this population of birds can change. We can have those that check in and those that check out. The check-ins are basically going to be births, that is hatching, whatever, but births, and emigration, individuals moving into the population. So these are additions to the population. The other way the population can change is checking out, as I call it. That is, individuals can move away, emigration, and individuals can die. That would also be a way of checking out. Therefore, the population size at any given time is related to the check-ins and the check-outs. And if you think of it in those terms, you can see that anything that would affect birth rates, increasing birth rates, decreasing death rates, increasing emigration, decreasing emigration, etc., could have an impact on population size. This movement, immigration and emigration, allows individuals to exploit variations in key resources and maintains populations' connections. Remember, populations may be in small clusters, as we talked about, not evenly distributed around the environment, but in clusters. And so dispersal allows for connection of these populations so that they are going to exchange gene pool and maintain the flow of genes from one group to another. This particular graph is simply showing over a couple of decades here what happened to dove populations in the U.S. and how they were able to disperse over the continental United States. The key internal factors in a population are going to be birth rates and death rates. We're going to, for the moment, sort of assume that immigration and emigration either cancel each other out or are not as significant, because I want to look at those for a few moments. For exponentially growing populations, we're going to see this kind of growth. That is, when individuals, let me rephrase that, I didn't really say that well. When a population moves into a new area, it's often going to experience exponential growth, as shown in this graph, where there's a latent period and then rapid population growth occurs at sort of astounding rates. If we look at this, we can see a couple of things here, but the key from all of this, and again, I know that some of you look at mathematics and get a little uptight. Don't worry. What I'm interested in is these last two equations. This is the change in number over time. So this is just dn dt, change in number over time, is equal to the birth rates minus the death rates times the number of individuals. This birth rate minus death rate is referred to as R, little r, lowercase r, and is referred to and is known as instantaneous growth rate or intrinsic rate of increase. So looking at birth rates and death rates, if birth rates increase and death rates decrease, the population will increase. If birth rates decrease and death rates increase, the population will decrease. In other words, the value of R determines what's happening as far as population growth. If R is less than 0, that is, it's negative, then that would be where birth rates are exceeded by death rates, that is, death rates are higher, then the population will decline. If birth rates and death rates, B and D, are equal, then R is equal to 0, and the population is stable. And if R is greater than 0, positive, because birth rates are greater than death rates, then the population grows. So the intrinsic rate of increase, or R, whether it's negative, 0, or positive, will tell us about what's happening as far as the population growth. There are some take-home points here then. The growth of a population is determined by the number of births, immigrations, deaths, and emigrations, check-ins and check-outs. Individuals disperse from one population to another to secure economic resources, food, reproductive resources, mates, or genetic resources, non-relatives with which to mate, and therefore decrease inbreeding. Dispersal leads to population connection or connectivity, and connected populations are less demographically distinct.